problem, this very first statement implies that m would be greater, strictly greater than 625. 25 squared being 625. Now, since we're talking about integers, maybe a nicer way of thinking of this would be to say that m is greater than or equal to 626, excuse me. M is greater than or equal to 626, right? Because we are talking about integers, and we have m strictly greater than 625. The next integer is 626, right? Or natural number, you might want to call it. Okay, now we want to know if these statements down here together or individually support this claim. Okay, so notice right here that if m is divisible by 50, an example would be 50 divides 150, right? 50 divides, and I use this vertical bar, it's convenient notation. 50 divides, say, 150. But you see, that's definitely less than 626. Okay, so I'll write less than m. M is just equal, or we'll just say it's 150 is less than m. Okay, so you see, 1 by itself would not be sufficient. So I'll put by itself, 1 is not sufficient. Allow me to abbreviate sufficient here. Not sufficient. Okay, so by itself, 1 does not meet the conditions right here. Notice I could use any other multiple of 50 that was less than 626. Now, in a similar fashion right here, we could do like 104, right? 104 is a multiple. 52 divides, I'm just going with low numbers, 52 divides 104. But again, we get the same kind of problem we had earlier. That's less than m. Okay. So that's, again, this one would also be not sufficient. SUFF. Okay. Now let's see, what we want to do is do some work that would help us out with regard to what happens if both are working together. What if both conditions prevail? Okay. Now it turns out it's useful to write what we call the prime factorization, because it allows us to compute very conveniently something called the least common multiple. Y'all, let me write that down here. So the LCM, the least common multiple, the smallest number that is a multiple of both 52 and 60, okay, the least common multiple would be equal to, we got to cover all the prime factors, so that would be 2 times 2 times 5 times 5 times 13. Okay, now notice this part right here is just equal to 100, and so this is actually just equal to 1300. Now, you could actually compute 1300 by inspection, but this nails it down. Okay, so that's supposed to be 1300, ladies and gentlemen. Let me erase that. Whoops. Okay, it's supposed to be 1300. Right there. 1300. But notice that the LCM is much greater. The 1300 is a larger number. Okay, substantially. Now I'll go ahead and explicitly write out 626 this time, okay? So 1300 is greater than 626, right? So by a long shot, if these guys are working together, that is, if both 1 and 2 hold, then definitely you're always, that's sufficient for it to support the initial statement. Okay, so in other words, what I'll say here is that 1 and 2 condition 1 and 2 together, 1 and 2 are sufficient. I'll go ahead and spell it this time if I can. Sufficient, C-I-E-N-T. Okay, let me circle that. Now, y'all, I hope that made sense. Again, all I did was show that if each of these were acting alone, we could produce multiples that were less than m. Okay, in both cases right here, we could produce multiples that are less than m. I produce 150 and I produce 104, which are multiples of 50 and 52 respectively that are less than m. So individually, they're not sufficient. But if you find their least common multiple, okay, that least common multiple is greater than 626. So that means that conditions 1 and 2 working together actually support the original claim. Hope that helped.